Hi, my name is Jim Kilty. I'm a science teacher at Tappan Zee High School. That is a school about 20 miles north of Manhattan. I teach physics. I teach a course on small engines where students learn how to tear them down and rebuild them. And I teach a carpentry course, which is kind of self-explanatory. For my physics courses at the end of each year, after the AP is over, I like to have a project-based final. And last year I was sitting down with one of my students, Cassie Bartels, and telling her how I wanted to do prosthetics. And lo and behold, she says, that's what my dad does, though. It was great. So I got a hold of Dr. Bartels, and we started talking about this. He came to our school, and he looked around, and I'll show you what he looked at. And he said that we were very well fitted to do what we had to do. The rest of what we did is going to be very student-oriented. They're going to show you different bits and pieces of how we did it from beginning to end. In fact, they drew a whole storyline on the whiteboard over here that ended March 13th, the day we shut down. So let me show you what we have. Before we got to the students, I feel it's good to show you around the classroom, where instead of having traditional desks, I have these whiteboard desks. Don't know how this will work this year because a lot of my teaching is through group work, where people coordinate together and learn to solve problems together. This is some of the equipment that we used in designing a prosthetic hand for a kid named Victor. The students have taken home what they needed of this, and they're going to make their own videos to show you how they incorporated this stuff. These are four of our smaller Dremel 3D printers. They're actually across the hall from me in a tech teacher's room. Mr. DeSantis, he and I kind of work together quite often, where I can help teach his class and he can show my kids how to use these machines each year. Works out great. Here is a room adjacent to his where we have more 3D printers. These two are quite a bit larger than what you just saw, and we use them to print out the palms. Here on the right, you see a Carvey. We have a larger one downstairs called X-Carve. It's basically, we use it for carving out wood. On the left, then, you see a resin printer, which uses, I'm pretty sure, UV light to cure the resin, harden it. This machine is in our shop downstairs. It is a Tormach 1100. It's a CNC machine. It just means that we could put metal in there, whether it's aluminum, steel, or titanium, and we could mill out any part that we can design in CAD and CAM on a computer. This led us to start to think that maybe soon we could start teaching the kids how to use this machine, or more kids, I should say, how to use this machine and design maybe prosthetic legs that can bear a lot of weight and stresses. So in case you don't know what CNC and all these letters are, this is actually a CAD program, computer-aided design, that we use. The kids, quite a few of them, know how to do this way better than I do. This is the CNC machine, the same program that we use for 3D printing. We can actually output to this machine and make it mill out anything we want out of metal. I wish I had something longer, but it is like a 3-second clip of it working. It's hard to see what's going on because it's cooled by a liquid that also lubricates. Left to right, there are 3 students here. You got Feta, Derek, and Brian. And Feta and Derek actually are in my shop class, but people get so into what this machine can do, I had to go fix some stuff, and they just wanted to do it themselves. They did a great job. On the right-hand side is Brian, who wasn't even my student last year. He was my student the year before, but he keeps coming back because kids love to do work with these things. Research and development and Victor. So here's where we get introduced to Dr. Stephanie Rand. She is in the middle, in the black dress, and the other 2 gentlemen next to her, those doctors, I only met them once, and I forget the name, but it had a lot to do with Stephanie, so I remember hers. They brought in a bunch of things for our kids to play with. They just have to play with it to get to see how these things even work. One of the things we found out was they are really difficult. It's really difficult to train a muscle here, like on this kid's forearm, that's Owen. to send out a signal to operate the servos that make that hand close.
How would I know what time?
And on the right, he's getting a little bit better at it. And next we have Brendan, who got really good at it.
Grab it. Yeah! Sort of.
3 students here on the upper left, they were doing research on prosthetics. On the right, you got Edith. He was trying to plan out how to actually lay out the things on the 3D printer to get it to print as many things at once as possible. And there's our first attempt at making a hand. It was functional. When we wired it up and pulled the strings, things worked. Okay, it wasn't our first thing we printed. We printed this huge finger, so we might have had a slight sizing issue there. These are a bunch of kids collaborating on what to do with the case that they got, the little kid Victor. So let's introduce you to Victor. And then after Victor, we're going to go back to that middle picture to what these kids were drawing there. I don't have permission to show Victor's face, so I had to smudge it out. But he has a left forearm slightly smaller, or shorter, I should say, than his right. He can bend it inwards somewhat with not too much strength, but he could bend it the opposite way with not only more strength, but more range of motion. So they collaborated together to come up with this, where they actually surrounded his finger with 2 mechanical fingers. The wrist was going to be strapped, the machine was going to be strapped to the wrist at the bottom of the picture. They were going to use gearing to create the motion in those fingers to close it. They were later on going to connect off the same gearing system, something to the thumb to pull that closed also. And if you look just above the picture to the left, you see that 50, 10, 5 in those circles. Well, that brought up the whole idea of gearing ratios, so they had to teach that to themselves. This is where I leave you, and the students take over.
After we tested different levels of the Arduino Nano boards to see how the different motors and sensors would function, we had to start printing different prototypes that we could try for Victor. We are really lucky that we have many 3D printers throughout our school, and we had a room right across the hall that actually had computers that we could connect to the 3D printer. So each student did research on different ways that a prosthetic could work. We tried gears, and then we ended up using like wires to build like tension to move, open and close the grip of the hand, and pins to keep it together. So each student kind of like picked what they thought would work the best, and everyone went on the computers, and we went on websites like Thingiverse, and Montefiore Medical Center actually sent us models that they tried to use to like print out, and they worked for them. So we wanted to try them, but we would have to print each piece individually and put it together. So it was still like our own. And then we had to transfer all the files to different STLs, and then we would connect it to the 3D printer and print them. And then for Victor's case, he had one finger in the middle, so we had to work around that to see which ones would fit his hand comfortably, and his hand works backwards, like stronger than forwards, so we had to figure out ways to work around that so that the model would be perfect for his specific case, which is different than everyone else's because everyone's unique. And then we inserted copper wires to keep the models together, and we had to overcome really a lot of challenges to build a final product. And even though Corona did stop us from getting to the end, I think we definitely would have got there. We were really lucky to have what we had and the supplies to try to build a model for Victor.
Hi, my name is Casey Kasulis, and today I'm going to explain how we use the muscle sensor to send a message through the Arduino Nano board to the motor that would react when the person using the prosthetic moves or clenches their muscle in order to move the prosthetic. So first we are working with these MyAware muscle sensor development kits. So this one's already a little bit set up, but upon opening it, you get a motor that we already have the screw in, and you put this on top, which will control movements later. And then we have the MyoWare LED shield soldered on to the MyoWare sensor, so that's attached. Next, we're gonna attach these electrodes to the MyoWare sensor. So and then we're gonna stick it to a muscle. This part has to go in the middle of the muscle, this side, and then this side has to go to the end of the muscle, and this is just really an extra support that goes on the side of the muscle. So when you put it on the muscle, you want to do it along with the muscle. So like I said, this part goes in the front, back, and then supporting. So I'll turn this on first just to show how this works. But basically, it just senses when the muscle is flexed or not. So right now. So it's not flexed right now. So when I go like that, it sends you a bar to show how much muscle movement there is. So when I'm fully flexed, it should hit the top of the bar. The kit also has this Arduino Nano board. So I'll show that. So you can see what all the inputs and outputs are on this side. And then these are already pre-soldered in, so we could attach our wires. So basically this is going to be what attaches the motor to the muscle sensor. So now we'll connect the wires to the Arduino Nano board, and you attach them based on what are inputs, outputs, and certain grounds. The Arduino Nano board that I'm connecting the wires to had been pre-coded so that it would transfer the message from the muscle sensor to the motor. And basically I'm attaching the wires to certain grounds, inputs, and outputs so that it produces the message to help the motor move once the muscle is flexed. So when we're doing this, once all the wires are attached and stay in place, let me solder it better. This should make the motor move, but when we had to leave school because of coronavirus, we never got to figure the wiring out perfectly. So this doesn't produce the right output even when it's at full flexing. It won't produce, it doesn't produce the full output. So we need 4 to 6 volts in order to make the motor move. And we were only getting about 1 volt. So if we had more time, we would have fixed the wiring and gotten this to move. And when the motor moves, so when we would do the muscle flexing, the motor would move. And once the motor moves, it would allow us to pull the copper wires that we put inside the prosthetics. So that would be the fingers. So that would be what allows you to clench your hand like this or release. But yeah, we didn't get to finish that because we didn't have enough time to correct the output.
The initial intention of the project was to find a way to develop prosthetics for lower costs. After reaching out to a local hospital, we received the case of a young boy who, due to a degenerative muscle disease, only has a single stump and 1 digit resembling a finger. Due to his young age, he will quickly outgrow any prosthetic device given to him in a short period of time. And due to that cycle and the high cost of prosthetic devices, It's unsustainable in the long run for his family. When I heard of this case, I decided to take it up as my senior seminar project and asked Mr. Keelty, my former physics teacher, to be my mentor. For my prosthetics project, I did a lot of extensive research on the field of prosthetics, and within that research, I found that the most important part of any prosthetic device is the interface. The interface is the space in between the skin and the device itself, and it affects usability as well as comfort. The means of attaching the device is what heavily affects comfort as well as the interface, and means include things like osseointegration, which is the direct fuse of bone to the prosthetic device. Due to children growing, such as the patient mentioned before, oftentimes osseointegration is an impossible move to a growing boy. Therefore, we need cheap, effective models that could be printed readily and designed custom-made for any dimensions of the kid. In doing this, I learned that for my design, I would use 3D printed parts to make them cheap and include a Velcro strap to make it easily taken on and off.
Hi, my name is Sarah Medujanin, and I'm currently going into my senior year at Tappan Zee High School. And I focused primarily on the software development for the prosthetic limb, specifically using this device called an Arduino, which took a lot of trial and error to get it to work. But essentially, after John had finished his general research on prosthetics, we began to get ready for work. So for instance, as I mentioned before, I focused mostly on the software part of it, but part of the preparation for the Arduinos for the prosthetic limb included some mechanical work on it. For instance, we had to solder certain pins onto certain places. So for example, I'm holding the sensor here, and in order for the sensor to actually work, it would have to be soldered into its respective slots, especially on the Arduino. So I definitely had to do a lot of research regarding those ports, not slots, rather. So yeah, so John and I we began soldering the pins to their respective ports using a port map that I created after doing quite an amount of research from online. And we definitely did run into a bunch of issues. Once again, it was trial and error. So, maybe we soldered something on wrong, or the metal just wasn't, or the aluminum was just getting in the way of the port or something. But we did run into a couple issues. But once we got the mechanical part down, we were ready to program the Arduinos. So another student who can't be here at the moment because he is in the Air Force. His name is Nico. He designed the proper code for the Arduinos with the help of a computer science teacher. And part of this code, it took in the amount of volts, for instance, that the sensor would have outputted. So say you flexed your arm and the sensor would pick up a certain amount of volts, and they would output that sort of to the Arduino, and then the prosthetic would move with respect to that. So that was essentially the code that Nico wrote. I took a look at it and I helped him out as much as I could with it. And I ended up having to upload the code to each Arduino. And once we had all of the code using this micro USB, once we had all of the code uploaded to the Arduinos, we began our work with the motors and attaching the motors to it. So once again, we had to solder the motors into their respective ports, which was also, once again, a trial and error. For example, the motor would not run. It wasn't getting a certain amount of volts that it required. So for instance, this tiny servo motor that I'm holding in my hand, it required roughly, I believe, 6 volts in order for it to actually spin and, do its thing. But the sensor was barely outputting anything. And we realized quite recently, actually, that the one of the pins was not in the proper slot on the actual Arduino. So it was a mechanical error, but once again, it's just trial and error. We just had to figure things out and get through it. We did have a couple faulty motors, which definitely ate up a lot of time in us, trying to make progress. But lastly, we did attach the servo motors and the Arduinos to the sensors on the arm, which you will see in a few minutes. And we began testing with the different levels with the Arduinos attached to the arm. So once again, the sensor would output a certain amount of volts that the servo motor would pick up, and the Arduino would run its code, and theoretically the prosthetic limb would work. So that's a little bit of my work that I did on the prosthetic limbs. Yeah.
My man John takes it to the next level.
So the moment we found out about this project, I was beyond excited. I instantly got up to get printer paper, grabbed my pen, and started drawing. That night when I got home, I made my first paper prototype, which we can see here. But we had to upgrade. So I got my wire, strung it through my hand, and we got working. So before we started making our own designs for prosthetics, we decided it would be best to do our research first. So we went online, downloaded some free files for prosthetic hands, and printed them to really understand how prosthetic hands worked and the type of ergonomics we would need to make them work. Speaking of ergonomics, we realized how important it was to have a high quality print, or else the hand would not be able to hold things correctly. Now, the design of the hand is only one part of the problem. The next part of the problem is making sure that the hand could actually move and function with the human body. For this, we had to program Arduinos and attach sensors, which detected the flexing of muscles in the arm. This would signal for the motors in the prosthetic hands to move the fingers. And so we finally moved on to designing our own prototypes to fit on our classmates' hands. And while we were so close to achieving our goals in the project, a certain pandemic hit the world. And while for almost half a year we couldn't make any progress, we're back and ready to work as hard, if not harder, than ever before.